Okay, so the idea of this video is not so much to go into detail, because I'll be doing that on the exam papers and the homework. I just want to show you how it's laid out and what we're looking for within this. So we're going to start with the difference between series and parallel. So there's two types of circuit. There's a series circuit and there's a parallel circuit. You can see these here. The thing with the parallel circuit is that the components are opposite, so they're not in the same branch there, whereas in a series circuit, series meaning one after the other, like I say, but the Netflix, you watch a program, and then you'll watch the next program, and then you watch the next program. So the components are going to follow each other in a series circuit, whereas a parallel circuit, they're going to be opposite. Now, there's benefits to this, which are not on there. If a bulb breaks in a series circuit, then the whole thing, just imagine this switch was closed, then the whole circuit doesn't work because that circuit is broken if a bulb breaks. And the more bulbs I add in a series circuit, the more resistance I'm going to be adding, so the bulbs are going to be dimmer within this circuit. Whereas a parallel circuit, there's benefits of, if you keep adding bulbs, then the actual resistance decreases, and we'll see that when we come to calculating resistance. But the bulbs say exactly the same brightness, so if I was to keep adding down, well, you can see in this image that those bulbs are exactly the same brightness there. And that's because the voltage stays the same throughout this circuit, and we'll come on to that. So the key things you need to remember for a series circuit is that the current in a series circuit is the same everywhere. So you can see that in here. So it's 4 amps there, and it's 4 amps there. And the thing with the ammeter, so it says current is measured in amps there, or amperes, and it can be placed anywhere, and it's placed in series. What that means is you place it just after the components, whereas you see these voltmeters here, the voltage across a component needs to be measured in parallel. So you couldn't just stick a voltmeter anywhere in this circuit. It needs to be across either a bulb or a component, or you could stick one over a battery. And again, we can see that when we come to parallel circuits, you know, if we're going to measure the voltage, it's the same. We've got to put it across that bulb, and then when we're measuring current, we use an ammeter, and we put it in series. We just put it within that. So notice how the ammeter is not coming over that bulb. So back to parallel circuits then, and so that we know the current is the same in a series circuit everywhere, but voltage, look, you can see that I've put different resistances on these bulbs on purpose, because like bulbs are like that. Some bulbs draw different currents, and you can see that even though the voltage is, so that it starts, you got 3 12-volt batteries, sorry. So that's going to add up 12, 24, 36 volts in total, because the more bulbs you add, the more power it gives, the more potential difference. Again, potential differences are just another word for voltage. You can see that if you were to add, and let me zoom in on this, if you were to add 8 plus 12 plus 16, it's going to come to 36, because the voltages add up in a series circuit, whereas in a parallel circuit, it's the opposite that happens. The voltage remains the same, and we can see that you got a 12-volt battery. This branch has got 12 volts. This branch has got 12 volts. Now, even though there's 2 bulbs here, there's still 12 volts running through the whole thing. It's just shared because these bulbs are now in series, aren't they? There's one follows the other, and we know that voltage gets split in series when it's shared in series, and that's why 6 add 6 is 12. So it's going to be, although in each branch, and we can keep adding branches, and it's always going to be 12 volts. But the current this time is split. So start with 15 amps, and then it goes down to 9 amps, and then it goes down to 3 amps. So you can think of these like little students. You've got 15 students here, and then some of them will go this way, and some of them will go this way, and some of them will go that way. And the reason it's 3 amps there and it's 9 amps there, there's a lot more amps there, is because of these 2 bulbs, okay? They're creating more resistance down here. If this was 1 bulb here, it's likely that all these would have equal values. So if that was, let's just pick a number 9, and then it would go to 6, and then it would go to 3. So you got 3 plus 3 is 6, and then plus 3 again would be 9, because they would be shared equally. So the main, to summarize that, in a series circuit, the current is the same, but the voltages add up. In a parallel circuit, the voltages are the same, but the current adds up towards the end. And that is the main learning there from those circuits. Then we come on to these standard circuits, which look like this. Okay, they look like this, and we need to be able to tell the examiner what we do, what is the purpose of this. You can see that the arrows are going this way this time. That's all that means. You can put these batteries either way, and then the current will either flow this way or either flow that way. You can see up in these ones it was flowing the other way because the battery was a different way around. Look, see? But that's all this circuit is used for, is to produce these graphs over here. Okay, you've got fixed resistors, you've got filament lamps, and you've got diodes. They're the graphs that we need to know. This is where we really want to draw your attention, because what we need to do, so this thing here, and by the way, you've got all the circuit symbols at the bottom of this page. What we need to do is to set the variable resistor. Now this thing is your variable resistor. This is just a component. That could be a lamp for all we care. That could be a lamp, or it could be a motor, or anything. And they've put a voltmeter over it, and they've put an ammeter in series. Look, so they've got one over the component, they've got one and the ammeter in the series there, and then they're going to adjust the variable resistor to see what these components like. So, for example, if this was a fixed resistor. So if this was a fixed resistor, we've got the graph for the fixed resistor here, and what they would do. First of all, we'd set the variable resistor to the lower setting, or the higher setting, it doesn't matter. When we did it on a PowerPoint, we set it to the higher setting so that it wasn't allowing any current through, and then we would slowly adjust it for voltage, and we'd pick that voltage up to 0.5, and then we'd measure the current, and then we'd take it up to 1, and then we'd measure the current, and then we'd take it up to 1.5. And what we saw was these lines. Now there's 3 lines here, and that's all that those lines represent, is different components, different fixed resistors, maybe different wires. The important thing to remember with this one, this is at a fixed temperature, so you're going to get that it's going to be directly proportional, and directly proportional just means that as one goes up in equal amounts, the other one will go up in equal amounts. Now that doesn't mean if this one goes up in 1s, this will go up in 1s, because it could be the case that this one goes up in 1s, and this one goes up in 0.5s, okay? But the principle is, for every 1 I go up there, it would be 0.5, and then if I go up another 1, that would be then 1, because it goes up another 0.5, and then if I go up to 3, then it's going to be 1.5, and so on. And these values will change depending on what type of resistor, what type of wire you've got. Now, the steeper the line, okay, the less resistance, because it's actually got more current for less voltage. So that's what these lines represent. Whereas if you've got a less steep line, it's going to be more resistance, because you've got less current up this side. So there's your current I for more voltage, and that's what that means. So back to this the standard circuit. We would set the variable resistor, and then as we vary the resistor, as we alter it, the current, it will allow us to take different readings. Now, for this case, they said as you vary the variable resistor, it alters the current flowing through the circuit. This allows you to take several pairs of readings from the ammeter and voltmeter. You can then plot them for current and voltage, like on a VI graph. So usually the voltage is the independent variable. The independent variable is the thing that we're changing, the choosing the value. So like I said, we're going up 1, 2, 3, 4, 5, 6, and then we would take those measurements of the current then, because that's on the y-axis, your dependent, the thing that you're measuring. This is a real common question. So there's a little bit of information there. Like I said, I don't really want to go into too much depth. I just want to show you where it is on these sheets. And then we've got that equation here, V over I times R. This really relates only to your fixed resistors and wires. because it's called Ohm's law, and it just means that they're directly proportional. If we notice with a filament lamp, it doesn't quite follow the same. So if we imagine the line starts here, that's all this is, by the way. Can I draw a line? The line should be, if I do it in red, and I don't want to confuse you, that's the axis there. And what we would have looked at is just sort of that bit I should have done there, where you've got that sort of F shape. Remember, for filament lamp, I said if you could just add that to it and it would look like an F. And what's happening here is there's going to be, as you start putting current through that bulb, there's going to be quite a bit of, as you start pumping voltage through the bulb, there's going to be quite a bit of current, but then the bulb warms up and it starts to tail off, and it's going to just become, the current there's not going to be any flow of current anymore, because even though that you're adding more voltage, the temperature is causing resistance. You've got all those electrons banging each other because they're more excited at higher temperatures. There's more activity. They're more likely to collide with each other. So there's going to be more resistance as we increase the voltage there. They're going to be more excited. And that's why it's important when we look at these fixed resistors, it needs to be at a constant temperature. And then we need to look at a diode. And before I do that, obviously I want to explain why sometimes you see this coming down that. Well, that's all they've done there is flip the battery around so that the electrons move the other direction, and you've just got a mirror image of this happening here. And that's why it looks like that. So you can imagine you got your negative axes here and your negative side there. So it's going to be 0, minus 0.1, minus 0.2, and so on. And it's just the inverse of that, really. Remember I was saying about the batteries, they can be flipped. So you can see this battery here, the current's going this way. But then we had a battery down here where the current goes the other way. So, and that's all that is saying, really. It's just a flipped version of that. But notice with the diode, it doesn't do that this time. It doesn't do that, and that's because diodes only allow current to flow in one direction. Okay, and it says the diode has a very high resistance, which is why it takes a while, even though I'm putting voltage, no current, and then all of a sudden it shoots up. And we call these, a diode is a semiconductor, not that you need to know that, but that's why they're really good at their job. That's why they're using TVs and the sort of little lights that you see on standby in the TV. Is because once you get to a certain voltage, the current that's produced is really high, and the energy is less. It needs less energy then, which is why LEDs they don't give off a lot of heat, and they're really useful. They don't give off a lot of heat as energy, whereas lamps do, and that's why we're changing now to a lot more LEDs. You see them in car headlights and things like that. So it only allows the current to flow in one direction, so you won't see this negative. Anything in the negative, even though they've probably flipped the battery around, there's nothing, and you can see that they're changing the voltage, but there's no current at all. And that's that page, really. And we're on 30 minutes. I'm going to keep going because this page is